back in chapter 2, we defined a complementary set to be the opposite set to the set we're dealing with. Or basically, if you're looking at a sample space, it contains a whole lot of stuff in it. My event is a subset of the full sample space. The complementary set is basically all the other stuff that's in the set excluded from the original set. And that's always represented with set notation by the bar or the line over the capital letter, which represents the event. So that's what Theorem 9.5 says. It says if A is an event and A bar is its complement, then, well, what this says is that the probability of the complement set is equal to 1 minus the probability of the original set. And this is a really obvious property once you get why. So let's kind of dive into this and see why this makes sense. So let's look at the example. It says list E bar, the event complementary to E, and calculate its probability. So in the previous problem 6, we defined E to be the union of E2 and E5. And actually, we didn't list that fully. So let's go ahead and do that. Basically, E was the set of all events containing either doubles or rolls of that added up to 8 or higher. And actually, I'm going to use my lasso once again to copy paste some of this so I don't have to write it all again. But basically, we did all the work to figure out all of the outcomes that add up to at least 8. So I'm going to drag those down here. And then I'm going to add in E. So that would be E2. And then I wanted to union it with E5. So E5 was all the set of doubles. That's a little bit easier to throw in there. And we don't want to cover duplicates, right? Because the union always excludes excludes those duplicates. So we have 1, 1. We have 2, 2. And we have 3, 3. And we already had 4, 4, and 4, 5. So basically our E set, which I didn't actually fully list before, but we've sort of figured out properties of it without it, contains all of these elements. And it's kind of fun to note now that we've listed them all, that it contains 6, 12, 18 total elements. So if you were to think about the basic probability, well, E contains 18 acceptable outcomes that satisfy the condition, which again, to return to, it's either doubles or when 8 or higher cumulatively would be rolled on those dice. And there's 36 total outcomes when rolling 2 dice. So we can see quite obviously that that's 1/2 of 50%. It's the same answer we got by using the generalized set combination theorem. But yeah, so in that, as I said in the last video, that's a different way to figure out the probability of particular events. You can always just go back to the basics and try to list every outcome to see what the probability would be. So now, however, what is E bar and what does that mean? So E bar always means the set complement to the set. And that's basically everything in the sample space excluding those. So basically it would be every die roll that is not doubles or that is not add up to 8 or higher. And, returning back to our sample space was all 36 of those rolls that we started to run out in example number 2. So like 1, 1, 1, 2, 1, 3. But basically, we'd want to throw out all of these and take everything else. So if you're starting with that chain, well, 1, 1 is included, but everything else that starts with 1 is not included. So, we'd have 1, 2, 1, 3, and we'd also want to exclude anything that adds up to 8 or more. But anything starting with 1 will not add up to 8. So none of those would be doubles and none of those add up to 8. And then I could move on to starting with 2, where we'd have 2, 1. 2, 2 is not okay because it's doubles. 2, 3, 2, 4, 2, 5. However, notice that 2, 6 would not be an acceptable outcome for this experiment because we're not allowed to add up to 8. And, I also noticed the pattern that there's 5 that start with 1, 4 that start with 2, and then so there should be 3 that start with 3. I would have 3, 1, 3, 2. 3, 3 is no good though, but 3, 4 is. I would have 2 that start with 4, so I would have 4, 1, 4, 2, and actually 4, 3. So I think I miscounted. And then I would have 5, 1, and 5, 2, and then 6, 1. But I confused myself there for a second, but I believe we found them all. But remember that if we're taking a set and its complement, the sum of those two sets' cardinality should equal the entire sample space. The entire sample space, there's 36 outcomes to rolling 2 dice back to back, 6 times 6, as we previously discussed. And so if I'm taking one set, its complement should always be the rest. This one was 18 elements, so as we already figured out, and its probability was half. But notice that the number of elements in the complementary set would be the rest of them. It would be the complete set 36 minus 18, or it comes out to be 18 as well. It's coincidentally the same. It's not usually going to be exactly the same size, but since the first set was half of the elements, the complement would be the other half. And notably, the probability of E bar happening, well, of course, it's always going to be the number of outcomes in E bar divided by the number of elements in the sample space. And that would be, in the same way, 18 out of 36, or again, 1/2 or 50%. So it ends up being the same answer. Again, just coincidentally, it's the same, but let's go back to Theorem 9.5, which I introduced the video with, and talk about why this is true. Oops, I did not mean to move that. So what it says is that the probability that the complementary event occurs is equal to 1 minus the probability of A. And the key thing to remember about 1 is 1 always represents 100%, because 1 in a ratio sense stands for everything, like the whole pie. 50% is half of the pie. And so how I kind of imagine this formula is, it's really the probability of a complementary set is always equal to 100% minus the probability of the original event. In this particular case, that probability that E occurred was 50%. So of course, the probability of its complementary event is what I like to call the opposite probability. It's the opposite from 100%. The original probability gave us 50%, so its contrary would also be 50%. But let's just say, for an example, the probability of this event ended up being 70%. Well, the probability of its complement would just be opposite to 130. So it's either going to be 70-30. And again, this makes common sense, because all this is saying is, well, this is the probability of something. This is the probability of the exact opposite. And if that something is some percentage that we know, the opposite is going to be the remaining percentage from 100, because it's either this or that. And those encompass the entire probability of everything occurring, which the probability of the entire event happening is always 100%, because if you took if every outcome was suitable, then your probability experiment is always successful 100% of the time.